Log on, tune in, find out. Another good idea from Cambridge.
Straight after lunch, 1:30, we have a poster session this afternoon, so I imagine the poster presenters will be hovering near their posters to answer any questions. Right now we have Rachel Warren. I should mention that unfortunately Rachel has to dash off right after her talk, so if you do have any questions for her, grab her before she disappears.
Give them a second to sit down.
Okay, so Rachel will be talking about the Community Integrated Assessment System.
Okay, thank you. Well, first of all, thank you for inviting me to speak here. It's a great pleasure to be here, and I very much regret that it's not been possible for me to attend the whole workshop, which I would very much have liked to do. Okay, I'm going to talk about integrated assessment modelling, and this is in the context of really making a link between climate change science and policy, and how we can assist those thinking about what mitigation targets we should set and also what adaptation needs to be done. So there are 4 sections to the talk, basically explaining what CIAS is and then talking about some applications, looking at how climate policy can avoid climate impacts, what is the role of avoiding tropical deforestation, something called the Wallace Initiative, and finally our web portal for users. So basically the background to this is that stakeholders, so this is like people attending Cancun, need to know the potential damages, risks and vulnerabilities in impact sectors that are associated with alternative future climate policies or carbon tax regimes. And they need to know what are those benefits compared with a case where there's no action to reduce climate change. And they also need an assessment of the uncertainties in these projections, preferably in the form of a risk assessment. And so basically CIAS was set up to provide this. Now almost the same needs arise in terms of those who need to plan adaptation, except that obviously they need to know much more about what's happening on a smaller scale and need to look at the full range of possible future emission scenarios in order to think about what impacts they might need to adapt to. So the Community Integrated Assessment System is actually a flexible, modular way of linking together different computer models that are written at different institutes and which are often written in different computer languages or operating on different platforms. So we worked with the Centre for Novel Computing at the University of Manchester and developed a novel system for linking these together so that we could exchange data and look at linkages and feedbacks between the models running at different institutions. It is possible to run them at different institutions, but in practice everyone's been quite happy for us to run them all at UEA so far. An important feature of this is that it's really geared up to look at uncertainty analysis in 2 ways. One is because it's flexible. We can swap one climate model for another, or we can swap a hydrology model for another. So we can try and understand how robust is the policy advice that comes out of it to using a different model. And also because we can look within the models at the uncertainty within them. And in particular, doing Latin hypercube sampling across probability distributions of various uncertain parameters. So I'm going to show you the web portal that the scientists use just briefly. This is where users control model parameters, set up uncertainty analyses, and view the output. The basic structure is a fairly simple idea, linking emissions to climate, downscaling it and feeding it to impacts. And ongoing work is to link those impacts back to the economy and then through to emissions. And this is a more detailed picture of the model components so far. So we are linking in a hydrological model, water stress and flooding predictors, energy demand model, that's the degree day, and the Wallace Initiative work, which is about impacts on biodiversity, and also a coastal impacts model, DEVA. And we also have an emissions scenario generator, which is controlled at this user portal. And what that does is that's where you can change the year that emissions peak or the rate at which emissions are reduced, and look at what rates of emission reductions lead to what improvements in climate change and its impacts. So I'm showing two web portals in this presentation. So this first one is the one that the team at UEA uses to access the system. And basically, so you this drop-down menu here is a list of all the possible integrated models you can run from it. So basically, you can run 2, 3, or 4 components together, or different combinations of them. And then basically, you can change the parameters in them, and you can also set up uncertainty analysis. So Robin Hankin, who's in the audience today, worked with us to set this up. And we have a number of empirical distributions that actually come from the literature. So all of the standard climate sensitivity PDFs from the literature are in there, for example. This is where we're looking at a parameter uncertainty in the MAGIC climate model. And then there are also various standard statistical distributions, and one which Robin himself has worked on called the Davies distribution. And basically then we sample across these, and this enables us to produce probabilistic projections of global climate change. Another way we can look at uncertainty is, rather than using the probabilistic model, we tune it to the 19 AOG CMs in the IPCC AR4 and the 10 carbon cycles in AR4, and thus we have actually 190 different possible projections. This is where the output is viewed, and coming online in January will be a very nice graphics viewer, but as it's coming online in January, I can't show it to you today. Well, that's where we've got to so far, showing just probabilistic output of transient temperature change for one of our runs. Okay, so moving on now to some applications. First of all, I'm going to talk about the AVOID project. AVOID is a consortium. It has its own website between Tyndall Centre, Walker Institute and the Hadley Centre. So I'm the Tyndall leader of that, and last year I led work stream 1 of that, and that was to basically produce information for DEFRA. DEFRA was in the process of becoming DEC at the time, to provide information for them in the run-up to the negotiations in Copenhagen. So we looked at a set of very stringent climate policy scenarios and compared them with one business-as-usual reference scenario. And we looked at what climate change is avoided and what impacts were avoided, and what carbon tax regimes were required to affect them. So we varied the year in which emissions peaked. We varied what the emissions were prior to the peak, the emission reduction rate after the peak, and the final emission floor that you could get down to. And basically we found that it was possible but extremely challenging to reach the 2-degree target for limiting global temperature rise compared to pre-industrial levels. Now I don't have time to go into detail showing you those particular results. Actually, it was the Hadley Centre who did a large part of that work. What I'm going to go on now is to talk about the impacts analysis that we did, which also involved members of the CIAS team. So the CIAS being Community Integrated Assessment System, which is what I'm talking about. Having got that output of climate change, either the probabilistic one or the 190 different projections, we then downscale them using a simple pattern scaling approach. Basically, there's a simple pattern scaling approach for temperature and a complex one for precipitation, which actually looks at the gamma shape distribution of rainfall, and it looks at how skewed it is. So there's actually quite a sophisticated work which has been done in the climatic research unit, which we apply here. And we project 8 climate variables, therefore, on a 50-kilometre grid, including sea surface temperature. And our results are at 0.5 degree resolution. And then those are linked to all of the various impact models that I was talking about. Some of them have to be disaggregated to give daily input. And we're actually in the process of developing a more sophisticated weather generator to do that. So locally, if you look at what's happening in an individual grid cell, obviously you can see that we've calculated the avoided temperature change in one grid cell for a couple of scenarios, but just to demonstrate to you that we really are, by applying these policies, reducing temperatures in these grid cells. And then we looked across all these different impact models and looked at the percentage of impacts that are avoided. So we calculated different metrics in each sector. So we looked at, for example, in water stress, how many people are exposed to water stress in 2100 due to climate change who would otherwise not have been exposed to water stress. And then we calculated that for each of the mitigation scenarios that we looked at. So if you focus now on, say, the red bars, you can see that the percentages of impacts that we came up as being avoided ranges between about 10 and 55%, depending on which impact you are looking at. Obviously, impacts that depend particularly on sea level rise, less of the impacts are avoided because of the very long time lag associated with ability to prevent sea level rise. So that's why, for example, coastal mangrove loss is difficult to avoid. You'll remember that I said we looked at variation in peaking date. So in this slide, we're actually comparing 2 scenarios where we keep the emission rate reduction rate after the peak the same at 5%, and then the date at which global emissions peak is varied. And so we found, both by doing this physical impacts analysis and by doing an economic analysis with another model, that the percentage of impacts avoided was greater the earlier that emissions peaked. And it was actually more important that emissions peaked earlier than that you increase the reduction rate later. So actually, the amount by which, if you delayed by 10 years, the amount that you would have to increase that reduction rate, you simply couldn't catch up according to what economists think. You would have to double the emission reduction rate later to make up for that 10 years loss delay in applying climate policy. And then similarly, this is just showing for one of the impact sectors how much you can avoid in terms of, here we're looking at biomes. So these are the way that ecosystems are classified across the earth. So forest, deserts, and grassland, and so on. And you can see that in the baseline case, this is the ASRES A1B scenario. You're having these very large transformations. They're not instant transformations. It's what you're committed to by 2100, not what actually is transformed by 2100. And so if you were to go for the, well, this is actually a stabilization scenario, but the 2 degree result is similar. So you could limit that as well by a very substantial amount, down to about 20-25%. We also looked at how much drought could be avoided. And so this is work carried out by Rita Yu, who's in the audience, and so she's doing her PhD with me, and she analysed she post-processed the outputs of the ClimGen model to calculate the SPI index for drought. That's a standard precipitation index that's very widely used. And basically looks at how much does rainfall in a particular month differ from the mean rainfall in that month divided by the standard deviation. So very, very simple basis. And then that's calibrated or normalized, as it were, to think about what actually defines a drought, how much deviation from the mean is a drought in each region. So for example, in the UK, you can look at how many droughts the Met Office thinks there have been in the last 50 years, and so that was used to calibrate that. And so the results of these analyses were used to calculate the number of months under drought conditions in an unmitigated case, so compared with a mitigated case and the observed case. So in the top left you can see observed climate, and this is counting up the number of months where there would be this SPI 12 drought, that is drought that has gone on for more than 12 months. And at the moment you can see that hardly ever happens anywhere has hardly ever happened anywhere for the last 50 years. Now if we project forward with the HADCM3 model, using that to downscale out to the second half of this century, you can see these absolutely huge projections of the numbers of months of drought going to over 300 all around the Mediterranean. And if you count up the number of months in 50 years, basically you're in drought about half the time in those red areas. We then looked at, well, what would happen if you went for one of the stringent emission scenarios, one of the most stringent ones you could do, basically similar to the most stringent of the avoid scenarios I mentioned earlier. And that actually does avoid a very substantial amount of those impacts, so see the bottom right. Rita also looked at the sensitivity to using a number of other GCMs, and although the pattern moves around quite a bit, the other ones that we looked at still show very large increases in drought in the Mediterranean, which is consistent with a number of other publications. Okay, so that was using CIAS to calculate avoided impacts. I'm now going to talk about another application of CIAS, which is looking at tropical deforestation rates. So the starting point for this analysis is that if you imagine that in the perfect world, which of course doesn't exist, you did apply those very stringent reductions of fossil fuel emissions. So you imagine that we reduce those emissions at 3% a year starting now. But you don't do anything about tropical deforestation. And if you look at the ASRES scenarios, which are widely used, they all assume that tropical deforestation actually slows quite dramatically. And a number of experts think that that may not be the case. So we did a sensitivity analysis looking at the two extremes. So no tropical deforestation at all starting now, through to all forests is lost at the end of 2100, and various scenarios in between, such as continued deforestation rates. And what we actually found, and what we then did, was we looked at the probability of achieving the 2-degree target or even a 3-degree target with those combinations. So very stringent fossil fuel emissions and different rates of deforestation. So basically we found that we had the probability of exceeding I think that should say the probability of avoiding the threshold, actually, sorry. Basically, if there's no deforestation, there's about a 60% chance of avoiding the 2-degree target and pretty much 100% chance of avoiding 3 degrees. If all the forest was lost, which takes you to about 4 gigatons of carbon emissions from the tropical forest over the century, then it actually plummets to less than 20%, and 3 degrees then has a 4 out of 1 in 5 chance of occurring. And then there are these various scenarios in the middle. If tropical deforestation continues at the rate of about 1 gigaton of carbon per year, you can see that it does reduce significantly the chance of staying below 2 degrees. So coming on now to the third application, this is called the Wallace Initiative. This is where we are linking the downscaled climate into bioclimatic models. There's one called MaxEnt, which is very famous, very sophisticated Bayesian statistical analysis, and basically uses the correlation between existing species distributions which are known and the observed climate to calculate relationships between where species are now and the climate. And it's amazing how well you can actually predict where species are by simply using current climate. So the first task in this study is actually to link the database of where species are with the observed climate, which we have from the Climatic Research Unit. And then we can move forward into the future and say, what are these projections of climate change that we've downscaled across those different GCMs, and where do those climate envelopes of all these species actually move to? Now, there's a lot of debate amongst ecologists about how fast species would actually move, and because that's a controversial area with a lot of uncertainty, we focus on mapping the refugia. Basically, the refugia is the area which remains climatically suitable in the future, and those would therefore be the areas where you would focus on protecting. So the idea of this is to help conservation organisations better design protected area networks, and so I'm working on this with Jeff Price at World Wildlife Fund US. And we are also looking at marine species and also wild crop types as well. Those are very important because they actually contain genetic diversity that can buffer modern crop species against disease and so on. And then finally I'm going to talk about CLIMASCOPE, and this is an initiative to develop a user web portal for CIAS rather than a scientist's web portal. So as you saw earlier on, that web portal I showed you was rather complicated for a stakeholder to use. So the idea of this is that we want to make the outputs of CIAS available to people for free, so that they can be provided with projections of future local and regional climate changes, and ultimately our projections of climate impacts as well, across a range of emission scenarios, including the new representative concentration pathways from the IPCC, which we're putting in at the moment, and the SRS scenarios, and some stringent mitigation scenarios that people might want to look at, and also providing some idea of uncertainty. So again, providing the 8 climate variables, annual, seasonal or monthly output, and users can then request mean output over a particular time slice of different lengths, or an annual time series, depending what they want. Of course, we're not giving them access to the codes, and every output has to be stamped with exactly its origin, all the right logos and so on, with the Global Commons license. And there'll also be the need to have some training. So World Wildlife Fund US has funded a company to build this site for us, and that's also expected to come online in January, so lots of things hopefully going to happen in January. And so this is just shows the user choices where they can choose the different GCM scenarios and the time slices and so on. This particular company that we commissioned to do it, they actually have a lot of other data as well, of all kinds of different, very, very different, not even related to climate science data that users could then overlay over the climate projections if they want to. So this is just an example of one of the maps. It's bigger than the screen, but it should say that it's a map of absolute temperature in 2050 for A1B. So unfortunately the scale and the title have gone off the screen. And then you can zoom in and look at Africa in a lot of detail if you want to. And then also the precipitation is available with some place names on it. Now, obviously, you want to look at uncertainty in these. You don't want people just downloading those maps and saying, right, well, this is it. So for that reason, we actually are designing a way that people would be given a small number of, say, 4 or 5 GCMs as an example, and Robin Hankin in the audience is working with us so that people will get scatter plots of all the 190 combinations of how much temperature and precipitation might change relative to now in their region. So basically we want people to be taught by this to understand what the uncertainties in the climate projections are, which is pretty important for adaptation planning. So in conclusion, what we are trying to do in the CIAS team is to provide policy relevant information to both adaptation and mitigation planners. And CLIMASCOPE will soon be providing free regional climate change projections with uncertainty analysis and scatter plots. And the whole system is based on this flexible linkage of models, which is actually unique in integrated modelling because most models are a pretty rigid, fixed linkage of different codes together. Thank you.
Time for some questions. I think Tim.
Well, it's an interesting project, particularly as you're engaging with stakeholders and such like. But that then leads me to a question about uncertainty and whether, you're looking at different GCMs, but are you taking, or are you thinking about taking into account, say, errors or uncertainties that exist across all of the GCMs? So I was particularly thinking about this when you showed some map of drought. And, if I was a stakeholder, I would want to know, can the current generation of climate models simulate drought that we've observed? So, if you looked at the spring, summer 2003, 1976, winter 2005, 6, other droughts that occurred, say, over Europe. Are we aware that any of the current generation of climate models can simulate that type of phenomenon? And if they can't, then how do you take that into, how do you discount your projections to stakeholders that take that sort of information into account? Because I feel that goes at a rather more deeper level than just polling across GCMs.
Yeah, well, I do have another PhD student who's actually been looking in the observed climate data and correlating them with drought to make sure that at least the observed data set we have contains the historical incidences of drought that has impacted on economies. And she found that they did. So there's a tick in that box. What you're saying about, obviously, processes that are left out of the GCMs, no, we can't there's no way of quantifying that in this. All we can do is accompany the projections with, you know, caveats which say, you know, the different GCMs are, you know, have varying abilities to reproduce the observed climate in particular regions, and we know that some of them are much better in some regions than others.
If you take
And
Europe,
then there's
for
also
example,
this problem that
are you saying that models can replicate the sort of more intense droughts that we've seen in the last, I don't know, 50 years or so of Europe? And by that I mean, you know, the circulation and the precip anomalies.
yeah, well, basically because we're using the magic climate model, and all our projections are basically adding the observed climate, and then we are calculating the change in climate and adding it on. So we're using the GCMs only to calculate those changes. Now, I agree that those changes may be suspect if the GCMs don't reproduce the observed climate. And, you know, I know that some of the GCMs are much better than others in Europe, but I haven't looked at that in detail now, and I would very much welcome, you know, if any those who are experts on this to provide some information that we could put alongside the other information to the stakeholders. If there are any particular warnings about particular projections in particular areas, then that's something we need to know.
I mean, if countries are potentially spending billions of euros or something on adaptation measures, I mean, these are important things to communicate, I believe.
Well, yeah, I'm not an expert on which GCMs work where. So, you know, that's what other people are doing, and I agree that there needs to be a link between that work and this work. Yeah.
I think we'd probably better move on with apologies to the audience. So thanks again, Rachel.